So this is a typical reversing valve or four-way valve, as they used to be called. Consists of a main valve body. It has a common suction port and then three other tubes which direct the refrigerant either to the outdoor coil or the indoor coil. It has a pilot valve and a solenoid valve. So if you have taken the NATE certification test for heat pumps, you may have seen a question like this. What effect does a low charge have on the switchover operation of a reversing valve? A. Low charge only affects pilot valve operation, not main valve operation. B. If a reversing valve is oversized, transfer will be normal. C. Reversing valves are less likely to transfer if the charge is very low. Or D. Charge has no effect on reversing valve operation. Many seasoned technicians who have been in the field for a long time have answered D. Charge has no effect on reversing valve operation. The correct answer of this question is C. Reversing valves are less likely to transfer if the charge is very low. So if you cut a reversing valve apart, you will see inside a slider and a trough that when the slider goes back and forth, it either directs the refrigerant flow from the discharge line of the compressor to the outdoor coil or to the indoor coil, depending on the mode of operation. Many technicians believe that the electric solenoid valve is what makes this slider move back and forth, when actually the pilot valve is actuated by the solenoid coil, and it directs the charge to one side or the other of the reversing valve to make the slider go from one side to the other. So most reversing valves are energized in the cooling mode. So you'll notice that in the cooling mode with the solenoid valve energized, the pilot valve has blocked off the discharge line, which is trapping the discharge gas on the left side of the reversing valve, causing the slider to move to the right. This then directs the high discharge gas from the compressor to the outdoor coil, which is in the cooling mode, rejecting heat to the outdoors, and the suction gas to flow to the indoor coil where we are absorbing heat. So then when we de-energize the pilot valve then blocks off the other side of the reversing valve so that the discharge gas is now pressing against the right side of the slider, causing it to move to the left. This then directs the high discharge gas from the compressor to the indoor coil, which is now our condenser, where we are rejecting heat to the indoor, and it allows the suction gas to go to the outdoor coil, which then is absorbing heat from the outdoors to put inside. There are four main types of failures in reversing valves. The reversing valve may fail switching from cooling to heating, or from heating to cooling. The valve may become stuck part way, causing gas to bleed from one side to the other, or it could be a refrigeration charge issue. The first thing you want to do is inspect the valve for physical damage. Never take a hammer to a reversing valve, as the valve body is very thin metal, and any kind of indentation or damage to the valve body could cause the slider inside not to slide. So the valve needs to be inspected to make sure that the tubes directing the pressure are not kinked or dented in any way, and that there's no physical damage on the main valve body. And also that the electrical solenoid coil is intact and is firmly mounted on the reversing valve. Then check for electrical issues. Is the reversing valve solenoid being energized and de-energized? Are there loose wires, or is the board not sending the signal to the reversing valve? And then lastly, check for refrigerant charge. If the system does not have a sufficient charge to move the slider, this could be the problem, that there is a leak in the system and there is not sufficient charge in the system to move the reversing valve. One method for checking proper reversing valve operation is the touch test. You'll notice that on these diagrams they have divided the reversing valve tubes to TP1, TP2, TP3, and TP4. On the left side, this is the cooling or defrost mode, and TP2 and TP3 is the gas, suction gas, coming from the indoor coil. TP1 and TP4 is the high discharge line going to the outdoor coil. So TP1 and TP4 should be the same temperature, and TP2 and TP3 should be the same temperature. On the right side, this is the heating mode with the solenoid de-energized. So now TP1 and TP2 become the discharge line, and TP3 and 4 become the suction line. The gas goes very quickly through a reversing valve, so the TP1 and TP2 on the right side should be the same temperature, and TP3 and 4 should be the same temperature. By taking these readings on a reversing valve, you can determine if the valve is shifting properly and there's no bleed by of hot gas into the suction line or vice versa. Diagrams like this have been available for many years to help you properly troubleshoot a reversing valve problem. They take into consideration the cooling and heating and which tube is supposed to be hot or cold. So make sure when you're troubleshooting a reversing valve that you have a diagram like this available to you to aid in properly troubleshooting the reversing valve issue. On most residential systems, the O terminal or B terminal are used to energize the reversing valve in the cooling mode. A call that we get commonly in tech support is, on commercial rooftop units, where is the O or B terminal to land my reversing valve signal? Carrier commercial rooftops commonly do not have an O or B terminal. The reversing valve is energized through the cooling coil internally in the control circuit. So on a commercial rooftop unit, when we receive the signal for cooling on the thermostat terminal strip, internally the reversing valve is energized, so there is no O or B terminal. So on a carrier commercial rooftop, you would set up the thermostat as a standard thermostat and not as a heat pump thermostat.
Go to arefco.com for more videos, like, subscribe, and check back every week for new videos.